Right then, so I'm gonna what do you call it? Condense my notes from the Conformations of cycloalkanes lecture, and these aren't just the notes from the lecture as well. I have made some of these myself, so there's a lot of content that I want to try and do in this video. Therefore, I'm going to be speeding through pretty quickly. Right then, so let's get into it. So cycloalkanes, their conformation is going to be determined by three things. It's going to be torsional, steric, and those two normal alkanes have, but since cycloalkanes like loop back on each other, they also have angle strain. And this angle strain occurs when the C bond angle, so that angle is less than, always different to, or should put that, should say it's not equal to 109.5 degrees, which it wants to be. Okay, right, let's just get straight into cyclopropane. So we're going to start off with a little diagram here. We're going to go like this, a little bond coming up to a H up there, and then we're going to go across. There we go. So I'm going to draw all the hydrogens on. I'm not going to draw all the carbons because I don't think we really need to. And the problem with this molecule here is that between these hydrogens, there's going to be torsional strain between these, and there's also within this molecule, this is quite an exceptional one considering the if we consider the angular strain. So this angle theta here, which is also equal to both of these other angles, I should point out, is going to be equal to 60 degrees, which is really, really small. And it's quite far away from the 109.5, which is why this cyclopropane is not very stable at all. And this is going to be due to the orbitals here. Is it orbitals? Yeah, there's these orbitals here. As you can see, the way I've drawn them, I'll just colour those in a little bit. There is really poor overlap between these two. So there's poor sp3 orbital overlap. There we go. So this is there's a lot of angle strain as well. Yeah, and that is due to the poor sp3 orbital overlap. Right then, so that's pretty much all that is about cyclopropane. So we're going to move straight on to cyclobutane. Right then, so this is quite a strained conformation. So if we just draw it here, I'll draw it out real quick. Boom, boom, boom. Try and do a 3D diagram. It's a bit challenging, but you know what? I think we can get through it. Like this, like that. There we go. Drawing on all the hydrogens just to be thorough. So these hydrogens up here and up here, there's going to be a lot of torsional strain on these two bits. So if we just write that torsional strain, and then this would then lead to this structure. So we can also say that within this one, if I just write down real quickly, this angle theta, and so the C angle is going to be equal to 90 degrees since it's a square. But in order to reduce both the torsional strain and the angular strain, or angle strain even, we're going to do something called pucker the ring, and we're going to change this into a bit of a funky looking diagram here. Oh, I've drawn that badly. There we go. There should be straight lines, but yeah, I haven't done that quite well. Oh well. There we go. Getting on all these hydrogens. Oh, how are we drawing this? I think I've done it a bit dodgy. Oh well. Doesn't matter. It looks something like this. But this will basically mean that this is called, so first I should have said this is this one on the left is the planar conformation of it, and this is going to be the butterfly. The puckered version is going to be the butterfly. And the way we've done this is there's going to be less torsional strain between these hydrogens, but the CCC bond angle is going to be equal to 88 degrees. So you have to note that we have gone from 90 degrees to 88, which is a bit annoying considering we want to be as close to 109.5 as possible. But the reduction in the torsional strain is a lot more significant than the increase in the angular strain, which means that it is worth it. This butterfly conformation is favourable. Yes, right, there we go. So we're going to move on to cyclopentane. Oh, goodness me, what have I stuck an I in there? Cyclopentane. So this is pretty much exactly the same as cyclobutane. So we're going to just draw this out here. Let's be thorough in how we're going to do things. Oh, that's gone a bit awry, never mind. So all these molecules, I need more practice drawing them. Oh well. I'm just frantically looking between my notes that I've got wrote down and trying to make sure I draw this correctly. Right then, so between here and here, you already know this torsional strain. The CCC bond angle is going to be equal to 108 degrees. This conformation, then again, is the planar conformation there. And as similar to the butane, we're going to pucker this ring again. So if we say pucker the ring, this is in order to reduce this torsional strain as much as possible. We're going to have this little thing here. Going to go up like that and up like that. That is no, actually not. It's not too bad of a drawing. I've done worse before. No, now we go down like that. All the hydrogens coming off. There we go. Right then. And this conformation, this is going to be called the envelope conformation. And the CCC bond angle is going to be equal to 105 degrees. So it's pretty much the exact same case as in the cyclobutane, because I suppose the only thing is we're pretty close to 109.5 with the 108. So I suppose this decreasing 3 degrees might be less. I'm not really sure. But not much to say about that. It's pretty much the exact same as cyclobutane. It reduces the torsional strain by such a significant amount that the slight increases in angular strain, it still makes puckering the ring favourable, essentially. Right then, so next one we're going to get on to cyclohexane, and this is a little bit different. Cyclohexane. Right then, so this is, we're going to start off drawing it as always. It's a pretty good place to start. Oh gosh, I have to draw these. I probably should have drawn all the diagrams out and then just annotated them in the video instead of making you sit. Instead of making my future self sit through me babbling on and drawing stuff. Anyway, right, torsional strain, you know it, between those hydrogens, always there. Torsional strain. Then again, this is going to be the planar conformation here, and in this instance, the CCC bond angle is going to be equal to 120 degrees. Quite nicely. Oh, I just dropped something. It's all right. Right, then here we go. So we're going to pucker the ring. Right, in this instance, oh dear, I hate drawing these. Let's see. Now, I know there's a way of doing it. So to draw these diagrams, we're going to do two parallel lines like this. Then we're going to make these into V's now. So we add on another line there, making it into a V. If you looked at it this way, oh, I'm crunching the paper. It sort of looks like a V. So we're going to do that for both lines there. We're going to try and get them as similar length as possible. Then we're just going to join up the remaining lines like that. Draw it like that. There we go. Right then, draw all these H's again, because I've done it for the others. I don't want cyclohexane to feel left out. There we go. Lovely. Right, the only difference, yeah, we'll call this one's the chair conformation. That one's planar, you already know. So the only difference with this one compared to the previous two is that the CCC bond angle is this one is 111 degrees. Now you can see it started off as 120. Now it's gone to 111. So that means there has been a decrease in so there's been a decrease in the bond angle, but since the bond angle started off above 109.5 and it's gotten closer to it, in cyclohexane there has been a decrease in both torsional and angle strain, because in the previous two, cyclobutane and cyclopentane, there was just a decrease in the torsional strain, and the angular strain increased slightly. But yeah, that's not the case for cyclohexane. So that makes this even more favourable, which is quite nice. Right then, I'm going to flip over the page, and I'm also going to flip over the page on my notes just to see what we've got going on next. Right, I'm just going to pause this just for a second. Okay, actually, I've just looked at my notes, and I think I'm going to call it there on that one, because I've probably made it about halfway through my notes on conformations of cycloalkanes. I know I sped through it quite quickly. I probably could have waited a bit longer and talked for more. But anyway, in the next video, we're going to be looking at a bit more on cyclohexane, and then we're going to be going on to like the bigger molecules. So we're going to be looking at the heptane and the octane and whatnot. So yeah, that's going to be it.